This video will continue our discussion of the cross product, applying it to a second scenario. So moving electric charges, either isolated charge or current in a wire, experience a force when they pass through a magnetic field. For an isolated charge Q, the force is given by Q times, which is a scalar, times the cross product of V cross B, which is a vector. So we'll end up with a vector where V is the velocity of the charge and B is the magnetic field, the force from the magnetic field. The magnitude of the force is that line there, where theta is the angle between V, the velocity, and B, remember, being the force from the magnetic field. Note that the sign of the charge also determines the direction of the force. So if the velocity vector is parallel to the magnetic field, the charge experiences no forces. All right, this makes sense because if it was parallel, then the theta is 0, sine of 0 is 0. The maximum force occurs when the velocity is orthogonal. This makes sense because theta would be pi over 2, and sine is maximized when it is pi over 2. If you would like to know more about this magnetic force stuff, please click that link. We're just going to use the math here. So imagine a charge moving through. It has a velocity vector moving through space, as we can see here, right? Moving through space. And then we have a velocity, or the magnetic field has a force pushing on our charge going this way. And the result of my charge, where it's going to move, would be where F is. So it's going to be pushed down. This kind of makes sense if you think about maybe like a swing almost. That's kind of how I think about it, where this is like almost connected and it's swinging that way. That's kind of how my brain thinks about it. That may be totally off, but that's kind of how I think about the charge pushing, or the force from the magnetic field pushing the charge in a new direction. Okay, so we're going to use that information to answer a new question. Okay, so we have this scenario down here on the bottom right. A proton with velocity 2, and it has that charge Q. We have that now, so we're going to need that in our formula. With velocity that experiences a force in newtons of that as it passes through the origin. So what they're saying is that as it's moving, this is F that it's experiencing. Like, this is the result from the magnetic field. It's not the force of the magnetic field. So it experiences that force as it passes through the origin. Find the magnitude and direction of the magnetic field. So that's B in this case. So here's our scenario. We're here, and we're moving along the x-axis, and that's my V. So I'm going to write V here. V is 2 times 10 to the 6th, comma 0. All right, we also need to determine, we have F. F has a J. We need 3 components here. So we have 0 for our Z. And then for F, we have a 0 in the I, and then negative 5 times 10 to the negative 12 for our Y. And then for Z, we have 0. All right. Above said theta is the angle between velocity and B. All right. Well, if I know that B is going to be orthogonal to both, then I know that theta's got to be a 90. Okay. So we're going to use now this formula to come up with, and we have it here, I don't have to keep scrolling up, right here, to find the magnitude and direction of the magnetic field at that instant. So let's go with, we have direction. We can go ahead and answer that. The direction is B. Well, B is moving in the negative Z direction. That's the way it's going to be pushed. Okay. All right, let's find the magnitude then. We have a magnitude definition. The force is equal to the absolute value of Q. We know it's absolute value in this case because it is 1 bar. This is the context thing that this is magnitude because it's a vector, times B, vector B, and then sine of 90 degrees, right, which is going to be 1. So we just have the inside of here. So we have 1.6 times 10 to the negative 19 times the magnitude of that is just going to come out as the same. because we only have one component, so it's 2 times 10 to the 6th times the b component, which we don't know, so we're just going to put b, because that's what we're solving for, and then that's a 1, and we also have the magnitude of f. So now we can use this to solve for b, which is what we want, the magnitude of that magnetic field. So I'm going to go ahead and multiply. Okay, 1.6 times 2 is 3.2 times 10 to the, and we add our exponents, so this is negative 13 times the magnitude of b, right? And then I divide, so the magnitude of b is equal to, and we do negative 5 divided by 3.2 is negative 1.5625 times 10, and then we do negative 12 minus negative 13, which is 1, so it's 10 to the first. We could leave it like that, or go ahead, I go ahead and write that out, negative 15.625, and our units, I think they gave us newtons. So that would be the magnitude of B. Now, B, since it is orthogonal, then we know the direction it is going. So we're just going to leave it at that. That is the force from the magnetic field. The direction of that is straight down, which we can see in our picture. All right, so that is dealing with electrical charge entering a magnetic field. I'm not going to hold you to a whole lot of this, mainly if what a test question could look like, potentially, I don't know. I mean, I do know, I guess, but I would give you like this. Something like that, I think, for anything like this kind of application. Now, applications like in the last video, simpler applications, the torque stuff, I would give you that information leading to it. What you're going to need to be able to do, for me, is apply it. Can you read all this and then apply it to figure out these two different things here? Can you find the calculus? So give yourself grace with these problems. They are very difficult because we are applying math to the real world for one, and then in calculus and algebra, we throw out a lot of the stuff that actually matters, like friction and all this stuff. Which is my downfall when I go to physics, because I'm like, this should work out this way, and it doesn't, because everything's approximation and friction and air resistance and blah, 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 all those different variables that mess up the math in a way. Okay, so that is electric charges moving through a magnetic field.